Welcome back, everyone. Thanks for joining us today for Neuroelectrics webinar. Today, we'll be talking about tDCS, transcranial direct current stimulation, or transcranial electrical stimulation in general, and epilepsy. So I'm very happy to welcome our guest speaker. We are honored to have today with us Professor Carsten Wolters. Hi, Carsten.
Hi, Rafael.
We are very happy to have you here, and we'll begin with Carsten's presentation, and then this will be followed by Q&A period. So please feel free to submit your questions at any time using Q&A tool. And please let me quickly introduce our speaker. So Carsten Wolters is a mathematician specializing in human brain imaging and modeling. He obtained his degree in mathematics with a minor in medicine from Technical University Aachen in Germany, and then earned his Ph.D. from the University of Leipzig, again in Germany. And he's currently leading the SIM Neuro Group at the Institute for Biomagnetism and Biosignal Analysis at the University of Münster in Germany. And his main research areas are the development of the new methods and applications for multimodal brain imaging and brain stimulation, to reconstruct and manipulate neural networks in the brain. So the field that is very closely linked to what we are doing at the Neuroelectrics, and we are very happy to have you here. Carsten, welcome, all yours, so you can start.
Thank you very much, Rafael, for the kind introduction and invitation. So I will share my screen. Oh, okay, thank you very much once again. So I thought I wanted to structure my talk. I want to start with an introduction. I explain a little bit about underlying methodology, both for the targeting that we do with electroencephalography and magnetoencephalography, then the optimization of multi-channel tDCS. And then I would like to evaluate the methodology in computer simulations and also in an experiment in a somatosensory group study, where we show that optimized and targeted multi-channel tDCS can outperform the current standards. And then at the end, I would like to show you an interesting case study in a focal epilepsy patient. And then we summarize, and I make some comments on software and an outlook possibly. So in order to introduce you to the topic, there's an interesting paper by a Chinese group, Yang et al. 2020 in brain stimulation. They stimulated epilepsy patients, and let's say in their methodology, the cathode is positioned always over the epileptogenic zone, and the anode of a bipolar stimulation is positioned far away. So this is their, let's say, the setup for the stimulation. Then they stimulate with 2 milliampere current, and they have 3 different groups. One group got only 20 minutes per day stimulation. The other group got 2 times 20 minutes stimulation per day. And the third group was the sham group. They did not get any stimulation. So they thought they get a stimulation, but they didn't get any. And they did that for 14 consecutive days. And they could show that the stimulation, both with the 20 minutes and with the 2 times 20 minutes, decreased the seizure frequencies. So SF is seizure frequencies when compared to the sham group. And they also showed that the 2 times 20 minutes daily stimulation is outperforming the 1 time 20 minute stimulation protocol. So remember, when I come to our stimulation, some of the parameters will be similar or identical to this study. I will come back to the study. So the point I would like to make is that very often targeting is only done by localization, by the location of something. For me, as an EEG and MEG person, the target is a vector. The target is a point, so it has a localization, and it also has an orientation. So it's a vector in the head somewhere. And with regard to so that is point number one, the target is a vector and not a location. With regard to hardware, the Chinese group and many others use standard bipolar stimulation. So one cathode, one anode, but nowadays, multi-channel tDCS hardware exists that bears the potential for improved effects. However, we need to know how much current should go through each electrode. So each electrode can get a certain current. It could get a negative or positive current with different amplitudes, and it is an optimization problem to compute these currents. So it's getting sophisticated. And there we are in the topic of targeted and optimized brain stimulation I will speak about today. So just to make an example, what might be wrong with a bipolar stimulation? It does not need to be wrong. Bipolar stimulation can be very good. But the problem is if let's say if the targeting is always done by positioning of one patch over the target area, yeah, with only with regard to location, and the cathode, for example, in this situation far away, in this case, it's a motor cortex stimulation, then it might be that the injected electric field by this bipolar stimulation, like shown here, in the target area is reaching the target area with a reasonable strength, but the orientation of the injected electric field is nearly perpendicular to the target area, and that might be largely suboptimal. Our goal should be that we find a stimulation setup that is not only, let's say, intense in the area of the target, but that is also oriented parallel to the target area. And this is the topic of my talk. So this is targeted and optimized multi-channel tDCS we will speak about today. One important point for such targeting and optimization is that we need head models. So we need to model individual heads. And if you are from the EEG and MEG community, what you mainly know is a 3-compartment head model. So this would be, for example, a simulation with an anode, with an anodic patch over the right auditory cortex and a cathodal patch over the left auditory cortex, simulated in a 3-compartment head model. And as we see, the current is a lot of current will flow over the skin compartment from the anode to the cathode. The current that is flowing through the skull is perpendicular to the skull surface. It is pointing inwards in the area of the anode, and it is pointing outwards in the area of the cathode, and it has quite a low strength because the skull is has such a low conductivity. And if we do not distinguish the tissues in the inside, the 3-compartment model only models skin, skull, and brain, then the current is quite homogeneously flowing from right to left. So nearly all cones that you see here, current cones, have the right-left orientation. That is due to the homogenization of the inner space. But this is not so realistic because our head does not only have 3 different tissues, but it has far more tissues. So if we would go up with our modeling accuracy and we would model now a 6-compartment head model, then we would have the following situation. So we have nearly the same in the outer compartments, like in the 3-compartment scenario, but inside we now distinguish the cerebrospinal fluid, which has a very high conductivity of 1.8 Siemens per meter, and gray matter and also white matter. And the white matter compartment, we model it as anisotropic. Yeah, I will later on show how we do that. So if we do so, we see that there are possibilities to use the high conductivity of the CSF to get also currents of a little bit larger intensity, a little bit deeper into the head. Yeah, let's say it is always related to the distance from the target to the sensors, but still we can make use to a certain extent of such channeling possibilities, like the result shows. And then what we also see is that the orientations of the cones in the inside can be quite different to the homogenized situation, because the anisotropy of the white matter fiber bundles has an impact on the orientation, and also the differences in conductivity of CSF, gray matter, white matter changes orientations of electric fields. And since orientation now plays a role, because the target is not only a location, but the target is a vector, so it has a location and an orientation, this might be important. So what we need is a good head model, which in our group, we always use 6-compartment anisotropic head models. Okay, so how can we on the targeting side? So first of all, we need to find out, let's say, where is the target, how is it positioned, and how is it oriented? And then we can compute such an optimized cap and go for stimulation. So how do we do that in Münster? We are in the good situation that we do not only have EEG, but we also have an MEG. So that is my basic research, let's say. I'm at an MEG lab, and we use both modalities for the targeting. And in this figure, you see sensitivity profiles of EEG and MEG. And what you see, so this has all been computed. So it's a certain kind of, the signal has been computed in a 6-compartment anisotropic head model. And the noise is real noise from a measurement that we added to the simulations. And if we have this set up, we can, in color, we can point out areas in the brain where the EEG is more sensitive. And then we can also point out areas in the brain where the MEG is more sensitive. The MEG is more sensitive to sulcal wall sources, so tangentially oriented sources that are on the sulcal wall, while the EEG is more sensitive to radial sources, for example, on gyral crowns. So here you see it very nicely. The gyral crown area is radially oriented. The EEG is more sensitive. Also the sulcal valley, the EEG is more sensitive. And all deeper sources, for deeper sources, the EEG is also more sensitive than the MEG. For the sulcal wall areas, it is the MEG that is more sensitive. So we try to use, in combined EEG and MEG targeting, we try to use these sensitivity profiles. So what we do is, from all subjects and patients, epilepsy patients that we are measuring, we measure T1 and T2 MRI images. We segment them in 6 tissue compartments: skin, skull compacta, skull spongiosa, cerebrospinal fluid, gray matter, and white matter. We model the anisotropy of the white matter compartment by measuring DTI, so diffusion tensor images, and we have an effective medium approach model that translates these water diffusion tensors into conductivity tensors. The measurement of the MRI takes 27 minutes. Let's say if you measure MRI of a patient, most often the planning that you need to do if you take only one T1 image is nearly the same as if you do 27 minutes measurement of T1, T2, DTI. So if you have the patient lying in the MRI, use a little bit more time to measure the 3 sequences, then you have all input information. The planning is not much more difficult to do that. And so we end up with an anisotropic 6-compartment head model. Now we come to something very important. The skull compartment might have different conductivities. So a head model is not only the geometry of the different head tissues, but for each compartment, we need to give it a conductivity. And for the human skull, it is very difficult to give it a conductivity because we all might have differently conductive skull compartments. So we have run a simulation here. This is a computer simulation. The upper row is MEG and the lower row is EEG. And we have modeled different skull conductivities. So the left column here uses a skull compartment of 0.02 Siemens per meter, and the right column has a skull conductivity which is 1/10 of this. And as you see, the MEG is not sensitive to skull conductivity at all, while the EEG is quite sensitive to it. So skull conductivity is important to know for all electric modalities. On the targeting side, it is the EEG. On the stimulation side, it is the TES. For the magnetic modalities like TMS and MEG, it is not. So now we would like to couple MEG and EEG, but we can only do that in a head model where the skull conductivity is accordingly, because otherwise MEG and EEG do not fit together, and the combination of EEG and MEG might be worse than modeling each modality alone. So first we have to solve the problem. If we want to combine EEG and MEG, we should have an estimate, a good estimate of the individual skull conductivity. And as we see, a low conductivity increases the distance between the positive and negative pole in the EEG compared to a higher conductivity where the distance is much closer. And we also see that the amplitude, of course, is higher of the two poles when we have the high conductivity compared to the low conductivity. We can make use of this. So we can use the MEG, because the MEG localizes sources accordingly, even if we have a head model with bad skull conductivity. And then we fix the location of that source and try to fit the measured EEG data and skull conductivity so that the source that we then localize explains in the best possible way EEG and MEG. And we do that with somatosensory stimulation. So here comes the experiment. This is me with an EEG cap and with an MEG helmet or Dua. I'm stimulated electrically on the medianus nerve, and we measure somatosensory evoked potentials and fields. We measure about 1,000 trials. That takes 7 to 9 minutes of measurement time. We do that with all subjects, epilepsy patients or healthy subjects with whom we would like to do brain research. And when we average those trials and we go to the 20 millisecond post-stimulus time point, then we find in EEG the P20, so-called P20 N20 component, P20 more frontally, N20 more occipital. And in the MEG, we see the let's say, nearly orthogonal topography of the so-called M20, magnetic 20 millisecond component. So now the calibration to estimate individual skull conductivity of my own head would be that we model the sources of the MEG. So we localize the source by MEG, and then we fit skull conductivity so that this source also in the best way explains the EEG. And we did this in a group of subjects, 20 subjects, and you see the calibration curves. Yeah? So each color is one calibration curve of one subject. On the x-axis, we have skull conductivity, and on the y-axis, we have the residual variance to EEG and MEG data when doing so. And the point, so it is, as you see, the curves are always nicely convex, which show that it can well be used, this procedure, to identify the best skull conductivity where the residual variance of the underlying source to both modalities, EEG and MEG, is optimal. And this is, we call this the calibrated skull conductivity. So it is a free parameter. I would not call it is the skull conductivity. That would be an overstatement. It is a free parameter that we adapt to the individuum, which then, let's say, makes it possible to use EEG and MEG combined in a source analysis of the data of interest, which might be, for example, epilepsy data. And what you also see is it's more reddish in the right area and more greenish in the left area. Greenish is older subjects. So I'm one of the older guys here. And we have younger subjects, which are more on the right side. So we could, in this neuroimage paper, show a significant dependence of skull conductivity on age, for example, which makes sense because when a baby is born, the skull conductivity is very, very high. Let's say 80 to 100 times higher than the skull conductivity of an adult. And it changes logarithmically over time or exponentially over time in a certain way. So in our head model setup, we use these somatosensory evoked potential and fields to calibrate the head model. Then now we have a head model that does not only have 6 compartments and white matter anisotropy, but it is also individually calibrated for skull conductivity. And this head model is then used for EEG and MEG targeting and also later for brain stimulation. Okay, how do we do the targeting? I will not speak a lot about it. It would be an own lecture of inverse problems. So in this case, for example, we have the M20, the somatosensory M20 in the MEG, and we have the P20 component in the EEG. And from both data sets in this calibrated head model, we would reconstruct Brodmann ARIA 3B individually with regard to location and orientation. And the remaining variance to the data can be expected to be between 0 and 20%. Yeah, so with this single source, we explain both EEG and MEG data with more than 80% goodness of fit. Most often even higher than 90% goodness of fit. This is our targeting, and we did this in a group of subjects in the next section. Okay, so let's come to the targeting and optimization. It is a paper that we published in Clinical Neurophysiology, which contains the methodology that we developed. We call this optimization the Distributed Constraint Maximum Intensity Optimization, DCMI. The functional, this is the only formula I will show, I promise. So what we try to optimize is that the vector S contains the currents that are injected over the electrodes. So the dimension of the vector S is the number of electrodes that we have for stimulation. And the A target operator is the finite element computation, the operator that maps the currents from the surface to the electric field in the target area. So for example, in this epilepsy scenario where we have this target area, the currents at the head surface that we inject would be projected to that target area, to this location of the cone. And then we have so this part of the formula would be the injected electric field at the position of the target. And it is a vector, so we can take the scalar product to our reconstructed target vector, yeah, to the orientation of that cone. And we try to maximize with our method, first of all, the intensity parallel to the target. We call that the directionality. So we try to inject an electric field that is parallel to the target, that is maximal with regard to intensity in the target area, parallel to the orientation of the target. And then we would like to do that in a regularized way. So we would like to use not only 2 electrodes, because if we would have this functional alone, we would end up with a bipolar stimulation. In fact, it can be even proven that this is the case. We would like to slightly regularize it so that we make use of more electrodes. And that is also important, as I will show later on. Not only with regard to reducing skin sensations and so on, but we only lose a very little bit of directionality, but use more electrodes that are available. It is much less tingling in the skin so that we can increase the level of the overall current. The level of the overall current is S total. So this term that we try to maximize, so if we maximize this, it means that this has to be minimized because there is a minus. So this additional constraint means that the overall amount of anodal current has to stay below a certain level. For example, for our epilepsy patients, we use 4 milliampere overall current. And this additional constraint here means that each electrode needs to stay below a certain level. And in our institute, we made a lot of tests. 2 milliampere current on the neuroelectrics GILD pi-stim electrodes was slightly burning, so that we decided, let's use a maximal current of 1.5 milliampere for the subjects, for the healthy subjects. The patients can get 2 milliampere per electrode because they want a treatment and they accept absolutely 2 milliampere per electrode. So we used 1.5 in the somatosensory experiment for the S-max-elec, so for the maximal current per electrode, and for the epilepsy patient, 2 milliampere. And if we use this optimization in different subjects, so S1, S2, S3 are different subjects, the different subjects have differently localized target Brodmann area 3B P20 components. So the P20 components, the sources of the P20 components have different locations, but more importantly, different orientations. As you see here, this is in red and blue, you see the measured topographies, and you see that subject number 1 has the P20 component over the left hemisphere. Subject number 2 has the P20 component in the middle, and subject number 3 has the P20 component even over the right hemisphere. Even if you think, oh, the targets are nearly identical, but they are not. The target orientation in this subject is pointing more to the right-hand side than it is pointing to the right-hand side in subject number 1. So the orientation is quite different, which means that we should also use different optimized montages, and that's also following Helmholtz reciprocity. So in subject S1, if we want to inhibit the P20 component, if we want to excite the P20 component, we should use anodic currents here, cathodes over the left hemisphere, like optimized here, in order to get the biggest directionality for this source. And for subject S3, the anodes should be over the right hemisphere, following reciprocity and following our optimization. And if we do this in 13 subjects, then, and if we plot, let's say, for our optimized and targeted procedure compared to the standard bipolar procedure, where we always use bipolar patches at the same positions, then we have a significant increase in the directionality. The directionality is this term, so it is the first term in the functional that we try to maximize. So our targeting and optimization leads to a higher directionality, and later on we will show that this also is measurable in the effect in an experiment. Up to now, it's only a computer simulation. Okay, so let's come to the evaluation study. So Asad Khan, who's now defending his thesis in summer, he did a somatosensory group study where he compared our targeted and DCMI optimized way with a standard bipolar stimulation and a sham stimulation. So the experiment was, in the first session, we targeted individual sources like shown, and we used EEG and MEG to do the targeting. When we had the target location, we optimized for the first condition with DCMI an 8 electrode, neuroelectrics 8 electrode setup that we used for optimized stimulation and also for the sham stimulation. And they can be distinguished by means of the time waveform of the stimulation. So in the real stimulation, we stimulate always, the stimulation is always on for 10 minutes, while in the sham stimulation, we ramp up and ramp down, and then there's no stimulation. And then at the end, we ramp up and ramp down again. What you mainly feel when you use 2 milliampere distributed over various electrodes or used in a 2-patch scenario with bigger patches is mainly the ramping in and ramping out. So this kind of sham stimulation works quite fine, as you will see later in the questionnaires. So we have 3 conditions: targeted and optimized brain stimulation with DCMI, standard bipolar with the standard 2-patch that are always positioned at the same locations, yeah, not optimized. You could also optimize them, but they are always at the same position. And sham stimulation, where we used the setup like in DCMI, but where we ramped down and did not really stimulate. And then, so that was a stimulation session for 10 minutes. Before the stimulation, we did an MEG measurement of electric finger stimulation, not mediano stimulation, but finger stimulation. I will later on explain why we use finger stimulation, not medianos. It's mainly because of, if you do it very long, it might be painful on the wrist, while it is not painful on the finger. So we preferred finger stimulation. We measured MEG before in the pre-condition, and then in 3 conditions afterwards. This time was needed for the subject to wrap with a towel the gel from the electrodes from the head and go into the MEG and get ready for MEG stimulation. Yeah, so there's a small red block, 5 minutes of time that were between the stimulation and the MEG measurement that we are losing, yeah, due to that procedure. And post 1 is then minute 6 to 16, post 2 is minute 17 to 27, and post 3 the last 10-minute session. And we always did finger stimulation and, let's say, generate a P20 component whose amplitude we can compare to the precondition. And if we do so, these are the results. And we could show that we have a significant increase in the targeted and optimized stimulation with DCMI optimized 8 electrode stimulation. This is, let's say, we keep the baselines always normalized at 1 from the precondition. And if you see something like 1.3, then it is the increase in amplitude of the post 1 stimulation amplitude compared to the precondition. So it's 30% more if that would be 30. Yeah, it's something like 25 or something. And then it goes down for the post 2 and post 3. It also goes down in the sham condition. Yeah, if we subtract these from the DCMI stimulation, we get even significance for all 3 stimulation blocks, and not only for the first one. For the standard bipolar, we have a slight increase, but it is not significant. And in some subjects, it works well, and in other subjects, it doesn't work good. Yeah, while in DCMI, we have, with the exception of 1 subject, it worked well for all other subjects. And we have large significances in our statistics that DCMI is outperforming sham or standard bipolar stimulation, while standard bipolar is not significantly when compared to the sham stimulation. With regard to the questionnaires, there is no significant difference between the 3 stimulations. So they did not, with regard itching, pain, burning, warmth, there was no difference. When we compare, when we asked the question, so which of the stimulations was now real optimized stimulation, which one was standard bipolar, which one was sham, then DCMI and sham could not be distinguished, as we see here. From the 13 subjects, 10 claimed that DCMI or sham might be real stimulations, and 3 claimed no, these ones were fake. The only difference is to the standard bipolar, and we assume that it was mainly due to the different hardware. They felt, of course, that, oh, they use salty water patches. This is a different hardware. That might be sham. Yeah? And this is why 6 out of the 13 subjects thought that the standard bipolar is the sham. So that they did not find it out. They cannot distinguish which one is sham and which one is not. And one last study of the group of Walter Paulus, where Assad and I were also involved. We did that with tACS instead of tDCS, also somatosensory cortex. And the figure here shows that on the x-axis, we see the angular difference. And the angular difference is the difference between the injected current vector in the target region and the source orientation vector. So if it is 0, then we have a maximal directionality. Yeah, and if the angular difference is getting bigger, like 45 degree would be somehow the maximum for tACS, that would be an oblique 45 degree orientation change that might lead to the lowest directionality. Now tACS, the orientation is flipping always, have that in mind. So 45 is quite bad. And what we see is that it linearly goes down the pre versus post difference of the P20 component, which shows that this effect is depending on orientation components. If we have a bad orientation, even if we have a big intensity in the target area, but if it does not have the right orientation, the stimulation might be largely suboptimal. So orientation plays an important role. Okay, so the case study in focal epilepsy, and then I'm done. How is it with the timing, Rafal?
No, we are fine. We are fine with the time. You have still time. No worries.
Okay, I think this goes quite fast. So we measured an epilepsy patient. We did the targeting with EEG and MEG. We see here the butterfly plots in MEG and in EEG of a number of spikes. In fact, we had more than 1,000 spikes of this epilepsy patient because the medicament was reduced and we had a lot of spikes. And when we go to half of the rising flank, where we still have a reasonable amount of signal compared to the noise, we see that, okay, we have a clean MEG topography at this time point. We also have a clean EEG topography at this time point. So it looks like the source is a little bit more radial than it is tangential, but it also has a tangential component. Otherwise, we would not have an MEG so clear. If we go a little bit earlier in time to -10 milliseconds, so where the onset of the spike is, there's a slight change in the topography, but it is only a very slight change. Let's say it's difficult to observe it here from the figure. You will see it in the localization. There is a little bit of propagation, but not dramatically. Still, due to the similar topographies, we use this very early time point because it is the onset and it is important to localize as early as possible in order to avoid propagation effects. We want to have the onset of the epileptic activity. We did the localization with EEG and MEG. The blue one shows the centroid of reconstructions for the EEG, the green one for the MEG. You see that the MEG sees tangential parts of the underlying patch, and the EEG sees more the bottom of sulcus radial parts of the underlying patch. And if we combine EEG and MEG, you get a source which has somehow a localization in the middle of those two and who has an oblique orientation between EEG and MEG. So it's the best centroid to represent the overall patch that is seen by EEG and MEG with different sensitivities. We, of course, for the stimulation, we take the combined one because we would like to get, let's say, the biggest amount of the epileptic patch that is underlying our activity localized from EEG and MEG. Retrospectively, that was not identified before. So our localization by EEG and MEG pointed the epileptologists and radiologists to this area where they observed a malformation. So this gray matter compartment is, let's say, not as sharp as it is, for example, on the other side, where it is very sharp. So they assume there might be a cortical malformation, for example, a focal cortical dysplasia that is underneath and that is producing the epilepsy. So we discovered something that was not known before. So a lesion close to Broca's area. The patient could not speak during the seizures. So when the lady gets a seizure, she stops speaking for about 20 seconds. And then, and this is the bigger problem for her, then she very often cannot remember what was discussed before. And you have to repeat what was discussed before. This is a big problem for her. So we optimized an 8-electrode cap and stimulated her with the neuroelectrics hardware with our DCMI targeted or EEG-MEG targeted and DCMI optimized 8-channel tDCS. You see here that now the cathodes are not directly over the target. They are a little bit more frontal to the target. Yeah. And let's say we use the maximum of -2 milliampere that we allow per electrode. That is what comes out of the optimization. So the ingoing current has to be very focal. So it uses 2 electrodes, the minimum it has to use in a frontal area. But in the occipital area, the algorithm is able to smear over 6 electrodes. So we have 6 outgoing electrodes and 2 ingoing electrodes. And it is a certain kind of banana, which has one closed end and one open end. Yeah, that's largely simplified, of course. Volume conduction is far more difficult, but it is a little bit message to take home. Yeah, let's say if the target is rather radial, then the cathodal side, where we want to inhibit the target, of course. This time we do not want to excite, we want to inhibit. So the cathodes should be quite focally over the target, but not directly over the target. It has to depend on the way the banana has to take. So the target has to be in the middle of the banana, and the banana should be closed at the target site where the cathodes are, and it can be opened on the other side without losing too much directionality. Yeah, and then it hurts a lot less in the occipital area, while it will hurt much more if we also only use 2 electrodes in the occipital area. So we decrease the burning and skin sensations. And then we did our experiment. We measured 1 hour EEG before the stimulation. Then we did the stimulation. You see the 2 cathodes here and the 6 anodes. 2 times 20 minutes stimulation, following the Chinese paper from 2021 or 2020. And then 1 hour EEG in relaxed but attentive state after the stimulation. And we always, okay, that's what we did. And we did that in 2 stimulation weeks. One of those stimulation weeks were active sham and one was real stimulation. That also followed the study of the Chinese group, but here we used only 1 week of stimulation, not 2. And so 1 real stimulation, 1 sham. And in fact, in our patient, the first week, since it's a first patient for us, yeah, it's a proof of concept for us. The first week was the real stimulation. The second week was the sham stimulation. And we had 5 weeks of washout between the 2 sessions. And then also on Monday mornings, we measured 2 hours of baseline for the baseline level of spikes in order to have a better statistic, but that is not so important. So what we then randomized the 1 hour EEG measurement blocks, and we sent these measurement blocks in a randomized ordering and in a completely anonymized ordering to 3 different epileptologists. They are colored with different green color here. And the blue color is the average over all 3 epileptologists. And that is now more important. You first of all see that they all do a quite different job. Yeah? Do not think that epileptologists all mark the same spike. There's a large variability. It's very difficult to do this job, especially in this patient who had very tiny spikes. What we see in average is when we compare pre versus post, that on day 1, we decreased from a level of something like 400 down to a level of 250. And then the second day, the level was overall decreased when she came. That was Tuesday morning. The level was already at 120 or 100. And then we decreased it to something like 50. So after 2 days, we had decreased the number of spikes from about 400 down to 50 by 2 stimulation sessions, or what happened in these 2 days. Yeah. Then on Wednesday morning, the patient came back and said, yesterday I had a seizure of reduced severity. I could not speak, but my husband said I could remember the discussion from before my seizure. So I give it a less severe, let's say the severity of the seizure was lower, much lower, because I could remember what was discussed before. So it was a slight seizure, let's say, a seizure of reduced severity. In any case, the level of her spikes at day 3 is this color, was up to 800 again. So on Wednesday, we started at 800 again. 1 day stimulation, it went down to something like 500, but still it was, when she came back the next day, it was still at something like 900. And then from Thursday morning to Friday evening, we could bring it down dramatically again. So that was Thursday evening. And then Friday morning is the yellow. So the yellow is again from 500 down to something like 100. So what we could claim is, with the real stimulation, we had 2 times an additive effect. On Monday and Tuesday, it added up. On Thursday and Friday, it added up. The seizure on Tuesday evening brought a lot of chaos into the system, so that the Wednesday, we could reduce the number of spikes, but it came up again at a very high level on Thursday morning. The active sham condition, while the real stimulation, if we look at single days, reduced significantly the number of spikes from 37 to 82% per day, the sham stimulation, the active sham stimulation, reduced from minus 22% to 36%. So it was sometimes increase, sometimes decrease. There was no significant change in number of spikes. Okay, there is a paper of Baut et al. I will make it very short. There are multidian and daily rhythms. And let's say we cannot explain our reduction in spikes by these cycles, because these cycles go, the multidian cycles go over 26 days. But what we could explain by the multidian cycles would be that the overall level of spikes in this week is different from the overall level of spikes in the second week. That could be explained by the multidian cycles very well, because it fits exactly to the 26 days of rhythm from peak to peak. So we have a fluctuation of spikes in any way, and we also have daily circadian rhythms. So during the day, the level is much lower than during the night. So that could also fluctuate between 10 and 100. But more importantly, if it goes down, if the level goes down, the seizures, which are marked in red, they are always when the curve goes up again. So in our case, it might fit. We reduce the number of spikes up to Tuesday, and then on Tuesday evening, the seizure came, possibly because the number of spikes went up again. So we reduced it artificially by brain stimulation to a very low level. Then it had only the possibility to go up, and then we came into the situation that the going up might produce a seizure. Okay, summary. EEG and MEG have complementary sensitivities and might see different aspects of source activity. EEG sees more the radial and MEG more the tangential parts. Combined EEG and MEG source analysis in realistic FEM head models that are calibrated can be used for activity target reconstruction. If you do not have calibration, a head model that is not calibrated should not be used for combined EEG and MEG. Then it might be worse. Then I would suggest to either localize only EEG or only MEG. Otherwise, the sensitivity profiles do not fit together. So you need to calibrate the head models. Individualized EEG and MEG targeted and DCMI optimized MC tDCS improved the directionality, that is the current parallel to the target area, and is a promising new approach that could significantly increase Brodmann ARIA 3B source activity in a group study with 13 subjects, while standard bipolar and sham did not. And it could significantly reduce epileptic activity in a focal epilepsy case study, our proof of concept, in a way which cannot be explained by circadian or multidian rhythms of interictal epileptiform discharges. It has to do with the stimulation. We have developed software. So let's say the Symbio project, which has also FEM code, has been developed. That was my, let's say, the outcome of my dissertation and an EU project, Symbio, in the years of 2002 to 2012. This software can do FEM simulations, and it is embedded into other open source toolboxes like Fieldtrip. It is also in commercial software packages, and it can be used, but it is a little bit an old software. It still has Fortran kernels for the FEM computations. So in the year 2012, when a new professor, Christian Engwer, came to Münster University, he's an applied mathematician, he brought the DUNE project to Münster, which is a huge toolbox for partial differential equation solving numerical solutions. And since then, I'm closely collaborating with Christian, and we developed the DUNE Neuro toolbox that has a lot of different FEM approaches, like the standard FEM approaches that other toolboxes also have, like, for example, the SymNips tool of Axel Thielscher, but it also has very modern FEM methods like unfitted discontinuous Galerkin or CAD-FEM approaches that are not available in any other software package. And we give this out for free. It's a free C++ code. It has no more Fortran kernels. It's a modern toolbox that is very modular. We give it also out with data that we have measured. So my data that I presented to you today is also available there. So you could redo what I presented. And this software is also embedded in other open source software toolboxes, like, for example, Brainstorm. And there's a recent neuroimage paper that describes that collaboration between the Brainstorm team, so John Mosher and Richard Lee in Los Angeles, and our group in Münster. And we here in-house, we also, let's say, DUNE Neuro has a Python interface and it has a MATLAB interface. So whatever Python or MATLAB software you have, or C++ software, of course, you can easily integrate DUNE Neuro for the forward computations. And the DUNE Neuro code is doing the forward computations, and the toolboxes do the rest of the brain research pipelining. Okay, so we have now, let's say, we fully stimulated 2 epilepsy patients. I've presented one to you. The second one is an evaluation. We have full data sets available. But this small EU project that is funded by the ERA PERMED for personalized medicine, in this project, we now try to increase the number of patients in order, let's say, the hope is that we get a statistic out of our results, because up to now, it's only a proof of principle. So single case is normally not, let's say, medical doctors will not take it serious if it is only a single case. And this project will hopefully help us to make a statistic out of it. And in this project, Neuroelectrics is a subcontractor. So we collaborate closely with Neuroelectrics in this project. And finally, an outlook could be that is a recent study of the same Chinese group that I mentioned at the beginning of my talk. They have now repeated these 2-week measurement sessions. They have repeated it 2 to 16 times. And each of these sessions was 2 weeks long. And they found an additive reduction in seizure frequencies and spikes. So it seems to be additive. The longer we do these stimulations, the lower the amount of seizures and spikes we will get it. Okay, thank you very much. I think I used a little bit too much time, sorry. And yeah, I'm happy for any kind of questions.
Thank you very much, Carsten. Really very very interesting talk with this methodological overview and with then real life clinical application. So we are open to questions. And let me ask because yeah, we are running at Neuroactics also the clinical trial, as you know, in patients with refractory focal epilepsy. We have some very good results in the pilot study. And in a case of your presentation, the question would be, you are talking about the target in terms of location and orientation. And we have also on the other side information that we are getting from the clinicians, from neurologists, from neurophysiologists, from neurosurgeons. They are someone defining the target in the classical way in term of epileptogenic zone, and what would be actually the target in terms of surgery. How you translate in case of the patient that you are presenting? Finally, you got actually the confirmation of the focal dysplasia there in the lesion. If there won't be lesion, what will be your target in terms of the information that you will provide to the optimization algorithm?
I mean, if let's say if the target cannot be described by location and orientation, yeah, I mean, what you get from the clinicians, they also do not call source analysis. They call it source localization. Yeah. The term already shows that they look for points in the brain and then they try to get intensity into that point. And very often it is not as focal as it is the case for focal cortical dysplasia type 2B, where we are focusing. So our project focuses on this kind of quite focal epilepsies. We have about 60 data sets of FCD type 2B epilepsy patients in EEG and MEG. And let's say the size of the epileptogenic lesion is between 1 square centimeter up to 8 square centimeters. So it varies a lot, but it is in any case very, very focal. So in these patients, if I would only know, if I had not measured EEG and MEG, and I would only know the location, for example, from a FLAIR MRI image, because I see that the cortical thickness is not appropriate, or that I see that the gray shade is a little bit blurred, and I expect there might be a malformation or focal cortical dysplasia, then I could do an intensity optimization. So if I do not have the orientation component, I could try to bring the maximum of intensity in that location and hope that there is a reasonable, let's say, orientation component, so that the effect is good enough. That is what I could do. It might lead to no effect, or it might even, in the worst case, if you assume a radial source that is pointing to the, let's say, to the electrode, and you are injecting the current in the wrong way, then you might even produce a seizure. So there's a certain risk, yeah, because we want to inhibit, and without any information on orientation, we do not even know if we inhibit or excite, and it would be a trial and error, yeah, strategy. So a little bit risky.
Okay. Thank you very much. This is clear. Let's go to the questions from our audience.
Possibly,
yeah.
I have to say one more sentence. Normally, let's say when you see a spike that is peaking over between two frontal electrodes, like in this patient, yeah, then you know if the source that is underlying has a more radial to the outside orientation, or if it is a source that is pointing inside. If you have a gyral crown area that is active, then it is a source pointing inside, because epileptogenic tissue is mostly pointing to the white matter compartment. If it is a radial source that is pointing in the other direction, you would see it with regard to the, let's say, either it's a negative or positive potential. So you would see it from the spike topography. and you might have a seizure collected in the EEG, and you would also know this information. So normally, if you have EEG, and you normally always have EEG at least, you know about the orientation. You have knowledge about the orientation.
Okay. At least from the interictal spikes, because yeah, we have to somehow differentiate interictal and ictal onset events, and ictal events that actually give more information regarding the origin of the focus, not only relying on the interictal that could be actually somehow misleading, because it doesn't have to show exactly the real generator of the seizure. But yeah, this is in terms of
possibly we have some other questions. So
sorry. So we have questions actually from Roberto and Eulalia regarding the conductivity. So you were explaining the importance of the conductivity, and there is a question from Robert: how does conductivity vary with age and post-teens? So you were explaining this in newborns or very young kids, the conductivity is much higher. How this is changing during life with age?
So our study of 20 subjects, which were all between 17 and 53, I think I was the oldest. For each age group, let's say you have a significant, the significance is a weak one, but you have a significance for age. So skull conductivity gets lower the older the subject is. We did not get any significance for sex, so female or male was not different. In each age group, we had a quite large variance. Most of our subjects, of course, are in the student age. So we had a peak in our statistic between 23 and 30, let's say. So our collection of data sets is not good enough to make a statement from baby age up to 70 or 80 years old subjects. But it's obvious that a baby has an extremely high conductivity because it hardly has a skull. It is, let's say, Fabrice always claims it's a membrane. It's not really a skull. And in the first year after the birth, a lot changes. The skull, let's say, gets a real skull. So I assume in the first year of age, the skull conductivity decreases significantly, and then it reaches a plateau and only goes down slightly. I think such a curve approximates the real life quite well. But the worst for us is that in one age group, if you have one 22-year-old student and you take another 22-year-old student, there might be still a factor 2 to 3 between their two skull conductivities, at least from our estimation procedure. So that in each age group, you have quite different optimized parameters. So that our, let's say, so we suppose that we should do this calibration in each subject in order to get rid of this quite big factor that you would have if you only use an atlas. If we try to build atlas values for each age class, one value, it would fail because the variance is just too high. So that is my message on this calibration aspect.
Okay, and I guess that this you can do with MEG with squids, and I know that you have available this OPM right now, optically pointed magnetometers. This you could do also with OPM magnetometers?
Yes, of course.
Because we are moving from squids to OPM, so this will be like more accessible actually way of getting the calibrated values.
Yes.
And so you were explaining, paying a lot of really attention to these details. I was thinking about CCF exactly, that we are acquiring during MRI in the lying position, and then in MEG you are doing the recording, and EEG actually in the sitting position.
No. We do all in lying position.
So you are doing this everything in the lying position.
Yes, it's very important because the epilepsy patients produce spikes when they come to peace. They need to be very relaxed. you know the circadian rhythms, yeah, the number of spikes is very low during the day and very high during the night. And we try, when epilepsy patients come to our lab, we tilt our MEG so that we have, the patients are lying, they are lying in the MEG with the EEG cap. They are very relaxed. We tell them, close your eyes and try to get into peace. If you sleep, even better. And this is how we do the measurement in EEG, MEG, and in MRI, they are also lying. So you have the same position.
The CSF factor, the thickness of the CSF is taken into account in this case.
Yes, otherwise we would have the problem that there's a paper of Rice et al. from Don Tucker's group. No, Rice from...
We'll check, but regarding the
Rice et al. Neuroimage, they show that if the level of CSF changes due to, let's say, prone and supine positioning, it might have a dramatic effect on visually evoked potentials. Let's say 80% in average change in amplitude if you are lying on the stomach or on the back. So the CSF has quite a channeling effect that I also showed in this one simulation.
Okay, and then comparing to electrical impedance tomography, would this be substitute for what you are doing for the calibration of the conductivity?
Let's say, I think if EIT would be available in a way that we all get ethical clearance, I would like to have EIT also and to compare EIT measures with our measure. Our measure is with EIT, let's say, from the theory, you could get skull conductivity here, and you could get it here, and you could get it here, and they will be all different. Yeah. What we optimize is a calibration, one single free parameter of calibrated skull conductivity for the overall skull. Now we are checking if we calibrate with somatosensory data and we compare it with the calibration in visual area, how different are these calibration values? And should we then use an average over them? This is all better in electrical impedance tomography, but ethically it's very difficult. First of all, we do not have the hardware. Secondly, our ethics committee might never agree that we do EIT with epilepsy patients. Yeah. Possibly this is less of a problem if others have solved this, then I would be very happy to use EIT, compare it with EEG and MEG, our calibration, and see if we, let's say, if we learn something from both of these measurements. We do it because it is very easy to realize in our setup. We have ethical clearance for somatosensory stimulation, no problem. I don't know if EIT ethical clearance for epilepsy patients exists and if we can ever do it in Europe.
Yeah, and this will be more challenging probably. Okay, so let's go to the question from Vikram. Actually, he's asking regarding your software. Is OpenMEG comparable to DuNeuro Symbio for forward modeling?
OpenMEG is from Maureen Clerc's group in Nice, in France. It's a very good software toolbox, but they use 3-compartment BEM modeling. So when you remember my figure with the 3-compartment head model and the 6-compartment anisotropic head model, their simulation would be like the left figure, yeah, because the BEM is much better if you homogenize the inner space, if you have 3 compartments. If you have 6 compartments and you model the real folding of the brain, it will introduce so many degrees of freedom into the BEM computations that it is dramatically increasing in computational, let's say the software is getting extremely slow. From then on, you can better do FEM computations. So if you, let's say the message is for 3-compartment head models, OpenMEG and DuNeuro get nearly the same results. Yeah, it might be a % difference with regard to numerical accuracy. There, this 1% is often, the BEM is better than the FEM by 1%. Yeah, for a 3-compartment scenario. But if we want to get a little bit closer to the real head, which has possibly 100 different tissues, the BEM is very limited. It is limited with regard to most implementations need nested shells. So the skin and the outer skull and the inner skull have to be nested. The compartments are not allowed to touch each other or even to cross each other. In neuro, with the unfitted approaches like CAD/FEM, we can do this kind of modeling that, for example, the brain touches the inner skull, which is just realistic. If you look at my brain,
the scale is correct. It's 1:1. The scale is 1:1.
That is 1:1. Yeah.
Okay.
And if you look at my occipital area, you see that I was lying in the MRI. Yeah, the occipital area is compressed, so I was lying on these areas, while here you have very strong folding. Yeah, and here it is compressed. Yeah. So the brain is compressed if you are lying in the MRI and if you are lying in EEG and MEG. So the compartments do not only touch each other, but they are lying on each other. Yeah, so you have not only one touching point, but you have a touching surface. And BEM cannot model that. We can model that easily.
Okay, you cannot get actually, so you assume that there is no, the tissue are not touching each other yet. So there is actually no way to model like the Bondaro effect, assuming that one tissue is touching the other tissue.
Yeah, these touching scenarios can, let's say, with the tetrahedral FEM approach, like Zimnips is doing it, you also can't model it. Because normally, in order to get high quality tetrahedra, the meshing tools like NetGen and tedgen, they normally assume that the surfaces are not allowed to touch each other. If you allow the toolbox to generate a mesh for touching compartments, the tetrahedra might be very misshaped, and misshaped tetrahedra might produce very bad numerical results. At least you have no more security for accuracy of numerical solutions. That is deep numerical mathematics. There's a danger of tetrahedra head models if surfaces are touching each other, but the brain is lying on the skull, and we try to model that in the best way possible. This is something that neuro has. It's unique, I think. Only in neuro these implementations are realized up to now.
Okay, thank you. Sorry, we are running out of time. I will only go through a few last questions to end up the one with Vikram. He was asking what was the inverse modeling algorithm you were using in your study, and it looked like dipole localization.
Yeah, very good question. So we use beamforming approaches, we use hierarchical Bayesian modeling approaches, but in this specific epilepsy patient, in epilepsy, if it is single focal epilepsy, like in this patient, we love to use dipolar approaches because we always can measure goodness of fit. So what we do is sub-averaging. We take the 1,000 spikes, we take 10 of them, we average the 10, we localize a source, and then we do that for 1,000 or even more 10 spike situations. And then we produce a cloud of dipoles from which we compute the centroid, and we assume that centroid is our target, yeah, the red point in the dart target, and we try to optimize our tDCS on that centroid. But we also have spread spheres, so we present to our neurosurgeons. So in fact, this epilepsy patient has got surgery in Münster, and I could look at it. It was an 8-hour awake surgery. And the patient is now seizure-free. So the diagnostics from our EEG and MEG were correct. They were also seen in invasive EEG later on. So first EEG, MEG, then they did invasive EEG. They saw that the result is correct. Then they did the surgery, and now the patient is seizure-free since February. Now we have to wait 5 years, yeah, until we really know if the problem is solved for her.
Okay, great, congratulations. And actually, you were not taking into account you were the eloquent area, because this was actually close to the epileptogenic zone was somehow close to the eloquent area. So you were doing localization of the eloquent area of the language, for example, too, with MEG for the pre-surgical evaluation.
Let's say the cortical malformation was grown into Broca's area. So within the surgery, they needed to localize Brodmann area 44 and 45. And then they stimulated. This is why they did awake surgery. They always stimulated first. So she had to name, this is a church, this is a chair. And if she could not, if she could not speak, the surgeon knew, okay, this area, I cannot cut it out. So he was always sucking out small pieces of cortex where he was allowed to suck out the small pieces of cortex. And he did not when the stimulation was in a way that she could no longer speak. So that was the awake surgery. What we always have to have in mind, we do not want to cure spikes. The whole brain stimulation in our patient worked well, because in FCD patients, very often the irritative zones where spikes are produced has large overlap with the epileptogenic zone. It is in fact identical. Yeah? So what we localized is the irritative zone, and sometimes the irritative zone is a sub-aspect of, let's say, the irritative zone might be a larger area than the epileptogenic zone. But what the surgeon has to take out is the epileptogenic zone, and it might not be identical to the irritative zone. This is something we always need to have in mind when we look at this kind of localizations. But the neurosurgeons, of course, know about it. This is why invasive EEG will always be needed. We should never only trust EEG and MEG. Our results always contain errors that we cannot avoid. Even in a 6-compartment model, we have volume conduction errors because the head has 100 tissues. We have a lot of noise. The spikes that we are reconstructing are irritative zone. They do not, the irritated zone does not need to be identical to the epileptogenic zone. So this is all part of the epilepsy puzzle. But from my experience in FCD type 2B, where surgery is possible to be done, the irritative zone is most often a very good representative of the epileptogenic zone. I presented only one case, but we have 1,000 case study that is now published in Brain by Stefan Ramp. Yeah, we discussed about it, Stefan, which shows that—
Regards to Stefan, by the way.
Huh?
Regards to Professor Hermann Stefan and to Professor Stefan Ramp.
Yes, right. So let's say we also have a statistic that in certain cases of epilepsy, the localization and the source analysis makes a lot of sense, even if we localize spikes.
Okay, thank you very much. Actually, so we go to the last question, and the question that we can not avoid today, and it's from Alan. Are there any specific artificial intelligence or machine learning technologies that you include or you plan to include in your pipeline? So yes. This is a question actually you will have to challenge.
So I consider myself as a beginner with artificial intelligence. So I have now, I had one master thesis in mathematics where I was the supervisor about identification of epileptic activity by artificial neural networks. And I had a student from Turkey, and Demet. So Demet is the name of the Turkish student. Now we are now shaping a paper where in the same patient that I presented to you today, we tried to run machine learning with a variety of different features, like you could use as feature alpha, beta, gamma band of the frequency, so different frequency bands, and then you will see that a spike 1 second epoch will be able to be distinguished from a non-spike containing 1 second epoch. There's also something like skewness, kurtosis, so statistical features of this 1 second epoch that a spike, an epoch that contains a spike will be distinguishable from an epoch that is not containing a spike. And then you also have something like Lyapunov exponents and let's say other features. And our paper is about, let's say our result is that if you train the artificial network with as many features as possible, take them all, yeah. Let's say artificial neural networks are, let's say, if they learn a lot, they know a lot, and then the sensitivity and specificity of localizing spike activity is fantastic, much better than the difference between our 3 epileptologists. So I think this is the most interesting for our epileptologists, is this new development that we are now trying to carry out, that they do no longer have to mark our spikes, because that takes them evenings of time, while a well-trained artificial neural network can do that very fast. But the training is now the problem. Yeah, in Europe, let's say, in order to train our network not only to this one single patient, so we trained with 90% of the data and applied it to 10% of the data of the same patient, and it did a fantastic job. How about we apply it to another epilepsy patient? Does it still work? So we need, of course, it will not work, yeah, because it has to learn about the next epilepsy patient, which is different. So we have to train the network by hundreds of patients, and then we need open data sets so that we can do the training for that network. So let's say, in summary, I think there's a good future for artificial neural networks to help epileptologists in marking epileptic activity. There's also future for marking in source space, because in source space you have much better spike waves than you have at the head surface, which was much better signal to noise. So identifying these with artificial neural networks is absolutely possible and already realistic, and is already done. But they have to be trained, and they will make errors. So it will always be a method. An epileptologist should use the method, and the epileptologist by him, so as a sensitivity tool, so the tool tells him, this might be a spike, please check. Here might be an epileptic activity, please check. Sure. And the epileptologist has much less work. He only needs to go through them and play the specificity and say, this is muscle artifact, this is a real spike. I think this will be remaining at the end.
Okay, so this is the future. Thank you very much, Carsten. Really very interesting presentation. Thank you all for joining us today. Again, thank you, Carsten, for being with us. We invite you all for the next webinar. And actually we'll have completely different topic, or not completely, but somehow from different field. We'll have Professor Silke Wolters talking about implementation of mobile stroke unit with extended capabilities that will include EEG actually in the mobile settings, but also radiography, ultrasonography, advanced laboratory testing, ECG, and Enobia with EEG in the routine emergency medical services. So this will be our next webinar. For more information, please visit our webpage, neuroleptics.com. Thank you very much. Have a great day, and see you next time. Thank you. Goodbye. Thank you, Carsten.
Thank you very much, Rafael. Thank you for the invitation, and see you soon.
See you soon. Yeah. Thank you. Thank you very much. Bye.